We all know that players in the IT world have changed. CPUs run the show and GPUs power AI workloads. But here's a problem. When it comes to analytics and real time data processing, even the most powerful CPUs and GPUs hit a wall. They were not built for that. And as enterprises go deeper and deeper into data, the infrastructure cost and energy consumptions are becoming unsustainable. So, what if there was a processor purpose built just for analytics? One that could replace 38 servers with just three. That's exactly what we are going to talk about in this episode of the Agentic Enterprise with Adi Gelvan, CEO at Speedata. Adi, it's great to have you on the show.
Thanks for having me.
Tell us about Speedata. What do you folks do?
We have designed the world's first APU, which actually is a chip that is able to run data processing on silicon.
We have all heard of GPUs, DPUs, and of course, CPUs. These days, when it comes to AI, everybody talks about GPUs and it's getting crazy. What exactly is an APU and why do we need something purpose built just like this for analytics?
Great question. So, 4 decades ago, we had only the CPU, right? Which is a general processing unit able to do everything from IO to printing to serial processing, whatever you need. Then was the era of the GPU, which started as a graphic processing unit, and today is the thing that is doing matrix multiplication for AI, because this is the basic instruction of AI. There was never built a silicon intended to do data processing. And nowadays, where you're looking at the AI revolution, data becomes the bottleneck. And an APU, which is silicon purpose-built to run analytics, is the solution for this period. So as AI scales, data becomes the bottleneck. The APU is here to be the next generation of the AI adoption.
Can you talk about the APU market right now? Is Speedata someone who pioneered it, or is it a bigger market and you are just one of the many players? I just want to understand the APU. I just want to understand the APU ecosystem right now.
There has been initiatives to try to create custom silicon or to create an APU based on general processing units. Most of them stopped with FPGAs, which is a field programmable device. And no one has ever tried to make a silicon or a custom silicon to run queries. We are the first ones. And when you look at the market, the analytics market and the database market, it's a huge market. And now it's become the bottleneck in the AI revolution. So this market has actually grown much bigger. And I think it's going to be 10 times bigger in the next decade.
You have put APUs in the market. Can you talk about how folks are using them? Were you seeing they are lowering dependencies on CPUs and GPUs, doing heavy lifting? Or are you also seeing use cases that you did not envision when you started working on APUs?
Great question. When we started designing the APU, the custom silicon, we thought about databases, ETLs, data lakes. Analytics is a very important market. We never thought about the AI market to be our target or AI use cases. Now, our silicon, we do not do floating point or tensor multiplication. We do SQL instructions on chip. What we realized is that where we build this to be data lake and databases silicon, we realized that the recent use cases our customers are using it is for AI pipelines. What we realized is that the GPU is great at training models, but the whole data pre-processing or preparation before you can actually train model, you need to go through ETL and do these heavy lifting on the data to make them be ready for the model training. So our customers, actually, one of our biggest customers today is a giant ad tech who is using our APU to pre-process data before training. And this use case, in this use case, he replaced about 40 servers with 3 servers, saving a lot of money, power, footprint, and his response times and times of processing is much.
I do remember that I talked to you a couple of years ago when you were CEO of SpeedDB, and now you are here at Speedata. Talk about your own journey.
Yeah, interesting question. So I made a career in storage, data processing, databases, being in database companies actually that have built databases trying to run on GPUs. And at some point, I realized that a GPU is not meant to do data analytics. It's very strong with AI. It's not good with data analytics. So I started my own company called SpeedDB. We've built a software library that was a storage engine, which means it was a database engine that accelerated performance of databases in software. We ended up selling it to Redis, which is now one of their flagship products. But this journey has taught me that there is a glass ceiling to how software can accelerate databases. And when I decided to join Speedata, which is doing it on the hardware side, actually designing a silicon from scratch to accelerate, that was my understanding is that analytics needs custom silicon purposely built to do SQL queries within the silicon. So for me, it was a natural next step to join such a company. And the reason I decided to join this is because I think that if you look at the future, it belongs to custom silicon, and analytics needed that. So happy to be here and lead this company.
When it comes to APU, can you talk about how they fit into the hardware stack of organizations? Is it cloud, like public cloud, AWS, Azure, whatever, or can you have it on your own data centers or even on-prem?
Yeah, so if you look at the history, servers used to have CPUs. Now, GPU did not replace the CPU. It complemented it. Now servers have CPU and GPU, and they both do different tasks, right? GPU does the general stuff. Sorry, CPU does the general, GPU does the graphics, and now the AI stuff, because it's purposely built to do tensor multiplication. In our vision, and we see this evidence with our customers, an APU is not replacing CPU or GPU because we don't do matmul, we don't do general stuff. What we are experts in is taking data processing, SQLs namely, and running them through the APU. What you get in our vision is that every server out there should have a CPU for the general stuff, GPU for the AI, and an APU for the analytics, which is the basis of AI. So a GPU will not be able to train models effectively if the data was not pre-processed very effectively. So in our vision, 10 years from now, every server has a CPU, a GPU, and an APU. And if you look at cloud providers, you see this very, very strong is that we are working today with some of the biggest cloud providers, and they are testing the GPUs with an APUs on analytics, and the results they're getting are staggering. An APU is much more cost efficient. We're able to run huge tasks on a very cost effective memory usage, power usage, and footprint.
Can you talk about the deployment of APUs? How does an enterprise actually gets the APU into their stack? Is it just another PCI Express slot, or they need specialized hardware to take advantage of APUs?
Right. So the chip that is sitting on a PCI Express card, which goes to any standard PCI Express, just like a GPU, despite the fact that it is much more humble with the power usage, and we are able to stack a lot of APUs in one server much than a GPU, and we consume less memory. So overall, if you look at the cost effectiveness of an APU in a server compared to a GPU, it's another world.
So it's not creating huge energy or power challenges, which is becoming a big thing these days. And it just works well in their existing stack.
It's actually a very interesting story. So, as I said before, it's a huge ad tech company. And these guys are using both CPU for data processing under Spark. They're also using GPUs on Spark. And they have started to test the APUs. And the test that was made initially, they took a production environment of 38 servers. And we took 3 servers with 6 APUs inside and moved the workloads from the 38 node cluster to the 3 node cluster. And we got about 50% faster results with less than 90% of the hardware. Think about it. From power consumption, from a footprint, and with that, we were 50% faster. So from this customer point of view, it's a huge cost savings. And now they're moving to replace a 1200 node cluster with less than 100 servers. So from this customer's point of view, huge cost savings, performance improvement, and footprint. So he can actually now put more and more nodes and servers in his data center without increasing the data center.
Earlier, you mentioned you folks target 3 distinct workloads: batch ETL, AI data preprocessing, and tag. Can you walk us through each and explain why purpose-built silicon changes the equation for all 3? And if possible, can you also talk about, as we mentioned earlier, it may be designed for a specific use case, but it can go beyond that. A lot of industries rely on analytics, whether it's financial, healthcare. Can you talk about these use cases as well? So there are a couple of questions put together.
Right. So batch ETL is the foundation, right? It's the classic ETL where you prepare data from databases to be in a data lake or in data warehouse. Right? This is the classic analytic use case. AI pre-processing is a new thing from the last decade, which you take data that comes from data lakes or from other sources, and you prepare it to be ready for model training. 70 or 80% of the time that takes before model training is the data processing. So these are new cases where still SQLs and data processing that you need to do before the model training. And the last thing we see today, which is the tag, table augmented generation, which is a very interesting thing. In enterprise adoption of AI, they don't use chatbots. They need access to structured data. The way an LLM is actually accessing structured data is by tag. An LLM is spawning SQL queries towards structured data, which is where the production data relies on. And that way, we're running those SQL queries, long and heavy queries, on custom silicon, on APUs. That's how we enable LLMs for the first time to access structured data very, very fast and enable enterprise adoption.
You folks also announced a partnership with Nibble to bring the APUs to European sovereign cloud infrastructure. A lot of talk is going on in Europe right now about that. Talk a bit about this engagement and why it matters. Honestly speaking, it may go beyond Europe because every region, even the geopolitical conflicts going on, honestly speaking, it may go beyond Europe because every region, given the geopolitical conflict right now, countries want data sovereignty, they want AI sovereignty. So, talk about the role of APUs here.
Very interesting trend we see with the sovereign clouds. So, most of the analytics worldwide was and is done on the hyperscaler, right? On the public cloud, Snowflake, Databricks, and the public clouds offering. But because of the geopolitical situation, um, many countries are investing in sovereign clouds where they can have the data reside within the country or within the continent. So you see many neo clouds or many data centers building their own data services for their customers. And Nebel is the first Sparrow. It's a Dutch company, NeoCloud, having many customers who are looking for managed data processing or data processing services within Europe. So we are building with them a full stack of data processing, model training using GPUs, and being able to do that much faster, much cheaper, and much more secure, not in the cloud, but within Europe. And we believe that this phenomena is going to go across the world. We see it happening also in Asia Pacific and in other countries. And yeah, we see a great future with the sovereign cloud.
Structured data is often known as the lifeblood of enterprise AI. Talk a bit about how accelerating access to it is critical for LLMs and modern workloads, and how analytics work in this setup.
Right. When you see the AI revolution, it started with consumers, chatbots, right? Growing very fast, and they're very cool. The problem is that the chatbots are not accurate. You will never get the same answer. You don't have predictability. In enterprise, when you want accuracy and you don't want hallucination, you need to access structured data of the data of the enterprise, which is stored in databases and structured systems. In order for LLMs to access this data, it's called the dark matter because the most important data of the world of the companies is actually there. It's not exposed to the internet. So the foundation models, the big models of ChatGPT and Anthropic with Claude were never trained on structured data. So for enterprises to use these models and to use these AIs for their needs, they have to have access to the structured data. The ability to access structured data in masses very effectively is relying on a very efficient hardware to do that. And that's where Speedata comes into play. Our APUs enable those companies to use LLMs with accessing their data. We mentioned that over tag. And that's where we come. And we think that the next stage of AI revolution is the enterprise adoption, which will need APUs.
This question may be a bit out of context, but I'll throw it to you. Since we are now talking about hardware, not just software, hardware means supply chain, something you have to manufacture. And we're also looking at shortage of GPUs and RAM, prices are going up. Talk a bit about who you are collaborating with to build these APUs.
Right. So you don't call hardware just hardware. You call it hardware because it's hard, right? It means that you have to deal with a whole set of problems, from inventory to actually designing a chip, which is a very long process, very risky process. And then where do you manufacture? Who do you collaborate with? So we are designing our chip. The R&D is in Israel. We work with TSMC, where we manufacture our chip, and then we assemble it, we test it, and then we ship it back to corporate. We put it on the PCIe card, which we designed by ourselves, and then we ship it to customers. So this whole journey takes time. And now recently, everyone hears about the memory cost issue, which actually makes hardware much more costly. Fortunately, the architecture of Speedata enables us to work with much less memory. So if you look at this hardware cost problem, in the long term, it'll be a great advantage for the APUs, as we'll be able to use a lot less memory, both on the card and on the server.
One last question before we wrap this up, and this is more generic and it's also hard to answer, is that when we look at all these LLMs, AI use cases, it is not going to go away. The cat is out of the bag. But at the same time, the amount of energy it requires, the cost, it is not sustainable. So, what are your thoughts on the new breed of hardware, APUs, CPUs, and GPUs?
It's a big question. I'm not sure I have enough perspective to give a full answer, but I do think that because data becomes the bottleneck to process this data, and even CPUs and GPUs, they consume tons of energy, and we've reached the point where the ability to adopt new models and AI relies on the ability to consume energy. If you see today, GPUs are not energy efficient. And if you use CPUs, you need to use a lot of servers, so they're also not energy efficient. In our view, the way that we've designed our technology is to be very, very cost efficient on memory, on footprint, and on energy. So I think that in that way, we will help sustaining this market, and maybe even help companies and huge data centers process their data more efficiently and enable the AI adoption, which is becoming a really big problem.
Adi, thank you for joining me and sharing these insights. It's clear that APUs are not just a performance play, they are solving real infrastructure, cost, and sustainability challenges in the age of data intensive AI workloads. So, thank you for great insights, and I look forward to the next conversation. Thank you.
Thank you, Swapnil. Happy to be here with you. Thank you so much.
And for those watching, if you're facing similar challenges around analytics performance and infrastructure efficiency, make sure to check out Speedata and its solutions. And don't forget to subscribe to TFIR, like this video, and share it with your teams. Thanks for watching.